Hello, welcome back to Intro to Cognitive Science. Today we are getting to a very interesting time in the development of cognitive science as a field. And that's where we will pick up and talk about the physical symbol system hypothesis. So, by way of recap, so far, what we've covered in this course kind of touches on this sort of broad exploration of cognitive science, the field, right? The very first things we talked about were kind of in this realm of answering the question, is there something unique here? Right? Turing machines were bringing together the idea of computation in a physical world. Deep syntactical structures from Chomsky are talking about how we can, there's clear evidence that we're processing something in our minds, not just the behaviorism of the world. And to that end, there were lots of findings that showed, hey, how would a behaviorist be able to explain this, right? So the idea is we are looking at something special, something unique, and then we pushed into, well, can we put some of these ideas together? What can we make of this? And so how do we detect some of this processing that's going on? How do we categorize it? Mars levels of analysis. Sherdlu was a model of all this, a computational model of language in a micro world. And then the mental imagery stuff. There were some studies that showed, there are resources in the brain that can be interfered with by requiring these different elements of a task. And then finally, more recently, we've been talking about how do things like these ideas of processing information and modeling and all this like idea of there's information flowing through the brain. How does that actually relate to the brain as we know it? So the emergence of neuroimaging techniques to help map different regions of flow, the idea of connectionism as an algorithmic answer to how the things that do exist in the brain, i.e. neurons, can achieve different processes in a computational, algorithmic sense, rather. So now we're coming to a new question of, as with any science, we need to define sort of the thing that is of interest to us, right? In biology, it's the organism. In cognitive science, what is it? Is it a brain? Is it a mind? Well, this is where we enter with the physical symbol system, the concept. It's not the only way to think about cognitive science, but it's a good sort of core idea. So let's see how that comes out. So 1975, Turing's legacy is this idea of having an award to offer to people who make significant contributions to understanding computation and the idea of information processing in general. And ACM, some of you may know of this, the Association of Computing Machinery, still alive and active. I'm actually a member. It's not prestigious; you just sign up. But I keep in touch with their active stuff. So the award this year in '75 was awarded to Alan Newell and Herb Simon. Big names. Newell and Simon are a major player in the whole breadth of cognitive science. Keep their names in mind. So they came together, and the way they achieved this, or rather what they achieved, was they put out a formal set of principles for studying an intelligent information processing system. Right? That's broadly the idea of a system that can process information like a human can. So this is founders of cognitive science, big part of the cognitive revolution. Just remember them, these two dorks playing chess in a lab somewhere. But it matters, right? They kicked forward some ideas of how to dissect our field and sort of make sense of it in a formal way. What does that mean exactly? Well, think about other sciences. So Newell and Simon come at this with the idea of, hey, we've studied other sciences. We want to take something away from how they operate, so we can tackle this weird, complex thing that's sort of amorphous. So they talk about the laws of qualitative structure. So the idea here is, in any science, you're going to be discussing things of a particular nature, right? It's not, in biology, I'm not going to be talking about cars. Why? Because cars don't have cells, right? So in biology, the core idea, the laws of qualitative structure talk about cells as the basic building block of organisms. In geology, we talk about what are the moving pieces in geology, right? Mostly it's just rocks. But there are things that move the rocks in geological activity, like at the core, but also large plate tectonics, right? So their idea here is, okay, we want to take, because all science is trying to study some kind of relationships, patterns, the way things move and change, mostly. So in AI and cognitive science, this is where Newell and Simon were coming at this, they came up with the physical symbol system hypothesis as the core structure that we study in this. So what the heck is a physical symbol system? Well, it ties two big pieces, big ideas together here in one sentence. It's a little dense. It's always hard to untangle these. So a physical symbol system has the necessary and sufficient means for intelligent action. So necessity, to unpack, is anything that is capable of intelligent action is, at minimum, a physical symbol system. So these things have the necessary elements. And sufficiency is any physical symbol system, anything that we call a physical symbol system, is also capable of intelligent action. More or less, it's just saying that these two things are bound inextricably. They are perhaps not identical, but they are mutually related, right? So a physical symbol system is the way that we achieve intelligence, and is also anything intelligent is a physical symbol system. That's the idea. That's a little vague, though, still. It's a nice guiding principle, and it's very important to the concepts here, but really we want to talk about what does this mean for how I approach understanding some kind of system, right? So here are the features of a physical symbol system. 1, symbols are patterns. Things that you can see in the world, maybe not see, sorry. We tend to think of symbols as, visual things, right? These words on the page are symbols. In any physical symbol system, symbols are like the core currency. So they are some kind of pattern, right? Symbols can be combined to form more complex expressions. If we're looking at this just as language, a sentence, right? A sentence is a set of symbols that have a more complex expression, a more complex meaning. Third, any such system is going to contain processes for manipulating complex expressions. We have to be able to do something with those expressions, right? As a physical symbol system, as an intelligent operator, I can't just see expressions and then do nothing. I have to be able to do something to them, process them in some way. But also, here's the really tricky part, those processes can also be represented by symbols, which can also be manipulated. I hope you're seeing how this is sort of coming together. Let me sum it up. So the system is capable of detecting symbols somehow, and then grouping symbols into larger, more complex kind of almost ideas, and then doing some kind of process on those symbols to change them and change their meaning, or make sense of them for a different transformed into a different form, whatever. And then also my process of transforming such things is also transformable, i.e. learning, right? We can change the way that the physical symbol system works. So let's look at some examples. Here's a straightforward one that you might not think of when we're thinking about, the goal is to think about how might a human be intelligent? But there are lots of physical symbol systems, just like there are lots of complexities of kinds of cells or organisms, right? So let's start with a basic one. Algebra. Oh, is this a physical symbol system? Yeah, it's a straightforward and kind of almost flat one, but it is. What are the symbols of algebra? All the digits, x and y. You remember algebra, right? Plus and minus, times. Whenever you are looking at an algebra equation, it is composed entirely of base level symbols. These things that you sort of learn their meaning and how they combine. The expressions are pretty obvious as full equations, right? And then the processes, how we can do things to those equations, i.e. solve them, or change their form, reduce them, those are all sets of rules, processes that take an equation and change it into something else that might be, say, more useful, or a better form to compare them against, right? So algebra it meets all the necessary conditions. This is a physical symbol system. Now, there's no brain doing you are the brain doing the algebra, of course, but there's no system that is alive sitting there doing algebra on its own, unless you count Wolfram Alpha. But this is the idea, right? This is one small, very simple physical symbol system that we can know kind of all the parts of pretty easily. On top of this, just a note that remember that the processes of algebra are themselves expressed in symbols. You can read about them in a book. You could also change them. Now we don't, because we all kind of agree that there's one specific way that algebra works well, and if we changed it, that would be kind of screwball. We don't want to change the rules of algebra, but they are changeable. They just probably wouldn't hang together quite as well. Okay, so this is a simple one. We can actually go even simpler, in a sense, and look down at formal logic instead of algebra. Formal logic typically is like dealing with the algebra of Boolean information, but ones and zeros, ons, off, truth, false, all that, right? So true and true is true, but true and false is false. That kind of stuff. This is a sort of reduced version of algebra. And if you remember from like geometry, doing proofs, if you've done any proofs in other places, this is the language of that. It works. It's the same basic idea. We've just kind of removed all the flexibility of the numbers and digits, right? It's just for ands, ors, nots, for all x possible, that sideways E, the trident thing. These are the sets of symbols in formal logic. The expressions are the statements of truth value, right? And the processes are the rules of deduction, the way that you flow through a proof to end up at a conclusion, right? We'll keep going. Don't need to harp on more formal logic. Let's talk about the digital computer. Okay, so digital computer is also a physical symbol system, and if you think about it, then must also be Turing machines must also be physical symbol systems. The idea here is the symbols in a digital computer are ones and zeros. They are on or off, right? The expressions are sets of those symbols, bytes, addresses, and instructions. Instructions to some system processor that will change those symbols, which the processor is executing the processes, right? The CPU machine rules of how one instruction can take the bytes in one area and the addresses of those bytes and move them and change them and adjust them so that you can save your Word document or print something to a screen or play a video or whatever, right? And those processes, we're getting to a place where we can, this is a fairly advanced physical symbol system because it has a lot of meta processes. You can change all of the bytes, all of the instructions, the way all of this works. Perhaps not down at the machine level, but this is a more abstract physical symbol system. It's capable of a lot more kinds of things. Let's talk about a weirder physical symbol system that you might not have considered. Chess. What? That's a game. What are you talking about? Chess is just a game. Why would this be? What does this mean? Well, let's break it down. The symbols in chess are the pieces, the raw symbols of how, of just what each piece is, right? We know that the knight is the horsey and the rook looks kind of like a parapet of a castle and all that kind of stuff, but those are just the raw symbols. It doesn't really matter what they actually look like. They represent separate concepts. The expressions are the full positions of all the pieces on the board. And the processes are the rules of each piece. So that if I want to transform one expression of the locations of the pieces on the board into a different expression of locations of pieces on the board, I will do so using the rules of the piece, right? I will move one piece, move the knight, it goes in a little L shape. Move the queen, it goes kind of anywhere it wants, right? So there are a limited set of processes that create the game of chess. We could, once again, change all the rules of chess, and I've seen a lot of things that experiment with this in fun ways, but we don't need to. It is still, at its core, even though it's not especially doing anything exciting or interesting outside of itself, it is still itself a physical symbol system. You can keep going up. AI, artificial intelligence, is an even more abstract physical symbol system than the digital computer, because it's the idea of complex algorithms going on at this sort of even more floaty level, right? The symbols are all the data represented within the system. The expressions are the more complex data structures that are, incorporate that data, like a database or a network between different concepts. And the processes are all the programs that exist to transform that data. You might notice I'm getting more abstract. I'm not talking about the raw physical details like a knight in chess or the symbol X in algebra, because these artificial intelligence systems handle much more robust and complex patterns. Their representations, the raw symbols and the expressions are just that much more complicated. But they still are expressible within the confines of the idea of a physical symbol system, which I hope you'll keep in mind as we jump to humans. Ooh, also complex and weird and fuzzy. But here we are. We can express human intelligence in a physical symbol system. So the symbols would be whatever the raw patterns of brain activity are that keep track of a symbol. So like a word or the visual pattern of the letter S, or a stop sign, right? The expressions are more complex thoughts and ideas composed of those symbols. Something means something else. This is related to this. I want this and desire this and need this and whatever. These are more complex expressions of the raw symbols of the brain. And then finally, the processes are whatever the heck we are doing to move that information around. We've talked quite a lot about this, right? This is what our brain does. It takes information in some form, some kind of expression, and it moves it and changes it and say in the visual system, hands it off to the spatial system or the temporal, identification system. These are the processes of human intelligence, thinking, or perhaps cognition, but the mental operations that are happening internally. So, I hope this has given the broad concept of a physical symbol system can be very complex and almost unknowable, or it can be quite simple and very explicitly detailed. This is the space of cognitive science, or at least under the physical symbol system hypothesis. This is the core thing that we should be talking about, is what they assert. So, the physical symbol system hypothesis brings us the PSS as the basic unit of any cognitive system, or rather the basic categorization tool for these systems. They can be more or less complex. Almost no one would say that chess is like a dog, right? But they still all adhere to the base principles of, hey, we're talking about information and how it changes. And we think of symbols as the core element of that information, and how can a thing do those changes in a way that is not just reflexive, but is more complex. So, and just like in biology, cells can be more and less complex, right? A neuron is extremely different than a muscle cell. Your organs are all different specialized cells, but they are still cells at the end of the day. They are still all following the same basic concepts and rules that make them cells. That's the same idea as the physical symbol system. So, what is thinking? This is the thing that we need to address, right? We said, oh, hey, the processes that humans use in physical symbol systems is thinking. What is thinking? It can be hard to pin that down as a thinking thing. So, one basic idea is that thinking amounts to problem solving problems. And intelligence, on top of thinking, being an intelligent system, is the way to work out the best solution when you're presented with a lot of possibilities and even constraints on what kinds of solutions you can do. So, this sets up the stage for, an intelligent process in a physical symbol system has to find sort of these minimums. It has to find the best solution. I think I've mentioned before, the brain is kind of lazy. That's because it's trying to find the best solution all the time. The fastest, the least effortful, the most useful, all that. So, and to quantify this, what is intelligence? What is the idea of being intelligent? You also need to consider the size of the problem space. So small spaces don't require a lot of effort to think through every possible thing, but a large space could be extremely large and extremely difficult to solve. So what we can take away from some of the classic AI to tackle this question is problem representation. So, in AI, typically, to make a system that is able to artificially and intelligently solve a given problem, we would need a good representation of that problem. So, a description of the scenario, what the available operations are for changing that description, some kind of goal situation to be in, and then at least tests to know if, hey, have I actually made it to the goal? So the problem space is the set of all possible situations from all these different choices you can make, right? So to be clear, we're setting the parameters of how, if we're going to assess something's intelligence in its thinking and its ability to solve problems, we probably need to have a good understanding of what problems even are. So they are a space of possible situations that you can be in, and all of the patterns, all the ways you can move through that space. Let's talk tic-tac-toe. This might help to lay this out. Tic-tac-toe it has a very small search space, but it still grows pretty quickly. So you have an initial state in tic-tac-toe, right? Empty grid. You, X player, have many possible places you can put your first symbol, right? Ways you can change the scenario. You can pick, so there's 9 possible, right? From each of those, there are 8 possible solutions for the O player. From there, more for you, 7, 6, 5, 4, 3, 2, 1, right? So you go back and forth until you have finished it. Now, you might know the trick in tic-tac-toe is you always go in the center, because there is always a counterplay from there such that you will either draw the game or win the game. There is no way, if you make all the right decisions, for the other player to win if you go in the center on your first move. That is intelligent, right? That's the intelligent choice. So we can know that at a high level, but the question is, how do we sort of, what are the parameters of that intelligence? How do we arrive there? Another example that I'll show you is, I think I've showed you before, the Tetris AI system, maybe on the first lecture. The artificial intelligence system that we wrote in my grad school lab to learn to play Tetris really well, right? And how does that work? Well, it starts with a single piece. It's going a little fast, but we'll talk about it. So it's playing the game of Tetris, right? But it's playing it in a weird way. It's not bound by time. It doesn't have to think about processing time. It's just comparing every available position for the block, i.e. considering every possible element of the or position in the problem space, and it's making some kind of call on, this is the one of those very many possibilities that I'm going to choose. You know, sometimes it has up to 40 possible positions to choose. It has to pick one. How it picks one, how it navigates that space, what it learns to do during the process of this AI training is examine the possibility space and make these calls based on features that it can detect in the space. For example, it doesn't want to make holes. You see at the end here, there's a little hole on the left. That's a pain in the butt, because that means that line is not clearable until you clear the one above it. Small things that a system must learn to make intelligent moves inside of its problem space. Similar vein, older and stronger, but although modern technology has outpaced Deep Blue. Deep Blue was a chess computer, and it started just as a big old tech demo, but they decided to make it into a hardwired chess player. And how does it do that? Well, Deep Blue is actually arguably not especially intelligent. It just brute force searches the entire 200 million situations, or rather, it goes as deep as it can. In chess, there are a lot of moves, and the complexity blows up really fast. If you go, hey, what are all the possible boards in 2 turns? It gets to be quite a lot. Deep Blue had some rules that helped it make decisions, because even with blasting through 200 million situations, just because of the speed of electricity, that would still be too few to solve the game at any given time. So it had to have some kind of pattern, or rather some kind of rules for searching the problem space. So this is the idea of problem spaces. And I hope it's easy to see how problem spaces can really blow up fast, right? Because in the complex real world, there's kind of infinite operations situations and ways to categorize things, right? If think about when you walk, just walking, right? There are lots of places that you could place your foot that are all kind of valid. They all work. Some of them might have you toppling over, but most of them. But there are so many ways to place your foot. You could angle it slightly. You could. So there are. It's hard to draw the lines of what is a meaningful definition of a problem space in the real world, let alone a single decision. So there must be ways to reduce this, both in terms of how we codify the problem, how the actual situation. So maybe it's not the exact all the angles of my limbs and stuff is my situation, but more how close am I to the midline with where I place my foot, right? So you can attempt to do a brute force search, but keeping in mind that there are a lot of possibilities, it can be really hard to complete a brute force search. So let's talk about the traveling salesman problem. This is useful. I mean, this is a useful concept because it comes up in all kinds of places. But it's an important thought. So, traveling salesman problem. You are a sales representative. You are trying to sell things. Woblets. It doesn't matter what they are. They're some kind of blob that you sell door to door, right? Or business to business or distributor to distributor, whatever. You travel around, right? You need to visit all the cities in the region to try to make your Woblet sales pitch and get paid for your work, right? You need to do this every so often. But you are a little bit strapped, right? You perhaps you have too many Woblets and you shouldn't have bought quite so many, but you're not going to waste any money on gas. You need to do this in the most efficient way possible. You must find the shortest path to visit every city in the region. So, try it out. Here is a traveling salesman problem. There are 5 cities, and there are colored, or, I mean, those just to help to separate to make sure it's clear, but there are lines, right? These are the paths. These are the distances in miles, let's say. Notice that they are all the same length, more or less, but they have different values. So just keep that in mind. Okay, so remember, you are the traveling salesman. You have to figure out the best path to save you the most money on your gas, because holy crap, things are hard. So pause this video for, I don't know, 5 minutes. Not even. Give yourself a couple minutes, 2 minutes. And start solving this. How will you do this? Okay. Pause now. And unpause now, I guess. Whatever. After you've taken your time, right? This is hard. This is kind of hard, right? It's not clear where you should start. But I'm guessing you came up with some kind of process, right? Assuming you took this seriously and tried it out, right? You came up with something. It's not totally clear what you did, maybe, on reflection, but you probably did things like avoid the 125s. Those seem like a long and unnecessary part of a journey when there's so many other options between these cities. You probably prioritize the small ones, but also, what direction did you need to start? So, yeah, the coming up with a path on this set of cities, you didn't do a brute force search, probably, right? That's a pain in the butt. You probably were not looking at every single line and saying, well, let me try all possible routes between all the cities, and then I will compare them at the end. That's not really how intelligent thought goes, is it? So this is where we enter into the concept of heuristic search. Problem spaces are often just too friggin' large for brute force search. This is where, Newell and Simon's second major point in their talk, right, that got them this Turing Award, is the idea that while the thing we are studying is a physical symbol system, these things are also typically engaging in heuristic search, not just brute force kind of dummy search. They are using some kind of set of learned information to make sense of a problem set and try to find the way to the destination, the goal, without exerting too much energy. So, in a sense, all heuristic search comes down to is the ways that you decide how to trim branches off of the problem space. That big decision tree, right? All of the possible routes, all of the possible chess moves, all the possible tic-tac-toe moves. You learn how to say no to even considering some of these, right? So in tic-tac-toe, a good heuristic is ignore all moves that result in an instant loss on the next move. But that is still something that you consider, right? When you are considering a move in tic-tac-toe, you recognize like, oh shoot, that leaves me open to lose next turn. That's a very simple heuristic, and it's very kind of stupid, like, oh, don't make the dumbest blunder, right? But it's still part of your decision process that says, no, don't even think about that. That one will lose you. This one will lose. This one will lose. In chess, a more advanced version of this is ignore all moves, and thus, again, all the other situations that could result from that move. Don't think about those. Don't traverse that search of the problem space. Anything that results in you losing a piece without, in turn, trading for one. Retaliation is what it's called in chess. But the idea of, if I'm going to take your knight with my bishop, or rather, sorry, if I allow you to take my bishop with your knight, I had better get something in exchange. If I don't, this is not a good line. I'm going to bail. I'm going to back out of this consideration and make a different move. I'm not going to get my piece stolen without anything in return. Now, there are, of course, advanced moves that would set somebody up for taking a free piece, and then maybe you manage to get them into check later, or whatever the heck, right? But that's why it's not hard and fast, but it's a set of competing heuristics that can all say, hey, there are lots of rules to this game, there are lots of problem spaces that I need to consider. Some of them are better than others. And this is what results in your strategy, right? The way that you trim your navigation of the problem space is the way your strategy is represented. So, using these methods, modern software actually beats Deep Blue pretty easily. The heuristic search is a stronger method of navigating these complex spaces than just kind of brute forcing it. Even if you have everything hardwired and it's just about the properties of electrons moving, it's still better to do heuristic search. So let's relook at the traveling salesman. We have 5 connected cities, right? So if you have any number of connected cities, n possible, right? N minus 1 factorial possible paths between those cities. Okay, what does that mean exactly? Well, think of it as 2 to the n. This is math, and I'm just hanging there. So if I have 10 cities, that's fine, right? That is still a lot. It's still a lot of possible combinations. To the 10th is like 1,000 something possible maneuvers through to get to the different cities, right? Different paths. But if n is 50, if I have 50 different cities I'm traveling to, even if I was calculating 1,000,000 possibilities per second, it would take 30 years to solve the traveling salesman problem by brute force, just checking every possible path between all the cities, every single one of them. 30 years. Let that number really hit. This is 1,000,000 possibilities per second. 30 years it would take you. That is not how you solve the traveling salesman problem. You come up with a set of rules that help you make each decision, and that is heuristic search. So, in conjunction with the physical symbol system hypothesis, we also have the heuristic search hypothesis, which is problems have solution structures, which are generated by coming up with processes and then modifying them with good heuristics. So the general problem solver proposed by Newell and Simon has some start state. This is where we begin in the problem space. Some end state. This is where we want to be in the problem space. Like, for example, winning chess or tic-tac-toe. And a finding process. Find all of the good transitions using something called means-ends analysis. So at each step, you are able to do something to figure out, am I closer to the destination than I was before, or am I further away? Is this a worse state to be in, or a better one? And this isn't the only way to characterize how you could build heuristics, right? There are lots of ways that you can put more complex things than just a single, measurement in. But it serves. It helps to come up with this idea of, well, okay, I want to combine features of my current situation to make an assessment about, is this good or not, right? This is adding a little meter to help us say, hey, here's where we should probably be going. I considered these three possibilities, and this one seems like the best scenario. Again, that doesn't mean that it will always lead to the best end result, but it does work. Okay, so I want to show you this fox and chicken problem, but I don't want to drone on too long here, so let's just give it a shot. Okay, fox and chicken problem. You have 3 chickens, you have 3 foxes. You need to take them across a river in a boat. If foxes ever outnumber chickens on a side, all the chickens get eaten by the foxes. How do we get everyone across? This is sort of a classic puzzle. It involves kind of lateral thinking about how to maneuver and how, I can move things in the boat 1 at a time, 2 at a time, etc. In this case, I think it's just 1, actually. But, okay, this is a classic problem in puzzling. And the idea is there is some combination of moves of animals to and fro the opposite sides of the river that will result in no chickens getting eaten by any foxes. I mean, ultimately, it's a stupid concept, but the idea is that it's not about the solution. I don't want you to waste too many thought processes on like what is the actual proper solution to this problem, but it's more about you can characterize the states of this particular task in a very reduced form. So how can we represent the states of fox and chicken in this fox chicken task? So the representation is F, C, and B, just 3 digits. This is the full state of the whole scenario. And F represents the number of foxes on this bank, as in not the far bank, but the first bank. C is the number of chickens, and B is the number of boats on this bank. So the start state is 331. The goal state is 000, right? No chickens and no foxes on this bank, and 1 boat on the far bank. Now, to change this state, to change this representation, this idea, this problem state, we have to have some set of permissible moves, right? Transformations. So, what are the possible transformations? I can move. Something important here is, I think I neglected to say this, the boat can carry 2 animals at a time. So the valid number of animals to move over at any given time is 2. So what are the things that work for those maneuvers? F can be plus or minus 2, and C can be plus or minus 0. So that would be move 2 foxes, either to this bank or the far bank. F and C can be plus or minus 1 each. So move 1 fox and a chicken at the same time. Or it can be 2 chickens, right? F doesn't change, and C is plus or minus 2. And then we also have the ability to move just one of them, right? We don't have to take both. We can take just one, meaning F or C goes up or down by 1, depending on what bank we're moving to and from. So on top of that, those are the valid moves, right? Those are the ways that we change the problem space from trying to get from our start state to our goal state. And we have constraints. We have some things that are not good because they result in a loss, a failure of the puzzle. So if F is ever greater than C, then that's too many foxes on this bank, all the chickens die. If 3 minus C is ever greater than 3 minus F, that means ultimately too many foxes on the far bank. You see, it's a little convoluted, but mathematically it still works. It's another check we can enable to say, hey, wait, have we failed the puzzle because we allowed this state to occur? And then also kind of important for if you're doing a search, if the idea is how to solve this, well, we want to make sure we've never had this exact same state again, so we don't end up backtracking and looping and doing the same move 20 times, even though it's valid, right? We want to progress toward the end state. This is how you would search the fox and chicken problem, strictly in this sort of reduced symbolic representation, which, as you might think, oh shoot, that's something that a physical symbol system would excel at. So the fox and chicken solution, it doesn't matter. It has something to do with moving only a single fox at a time, and then a bunch of pairs, all that kind of stuff. Offset the numbers so that they can't be overwhelmed, something. That's not the key point. The key point is that we have built a problem representation that can be solved algorithmically, which is something a physical symbol system is defined to do. So we've got a physical symbol system can operate on these reduced forms to solve the problem, right? So that's the big idea. Physical symbol systems and heuristics together make this idea of how a symbol system in the world, a physical instantiation of a symbol system, given its properties, can solve many problems. Now, it's important to think of this. This is a pretty reductive way to look at intelligence. We are boiling everything down into raw, neat, tidy, small symbols. That's not how everybody looks at intelligence. Just need you to understand that. But it does seem likely that we are able to at least do these things, right? We are able to maneuver ideas in our minds in these ways. So, at minimum, these things are possible for a human cognitive system to engage in, but not necessarily the end and be all of that. So, this is neat. It gives us this great way of characterizing the basic phenomenon of cognition, sort of this moving information around in these chunks, in a really robust way. It has different levels of complexity are possible, different definitions for what make a pattern, all that stuff. So physical symbol systems solve these complex problems by manipulating the symbols of the problems, right? Changing the fox and chicken values internally, updating them, looking for a good solution, and using actually better heuristics, not just brute search, but smart heuristics to try and narrow down that search and guide it towards the best solutions possible. Doesn't mean you will always find them. Sometimes you'll get stuck, and I'm sure that happens in your brain all the time. That's life. But these are thought to be the kind of core elements. So, From here, we'll expand on the physical symbol system hypothesis by looking at the language of thought hypothesis, which I think is very cool. And then later on, we will look at whisper as an example of symbols as image representation and processes as sort of physics simulations. How we could do something as complicated as sort of a physics process entirely in symbols. Okay, that's it. So that takes us to our final thought. What are some other things in life that could be considered physical symbol systems? Keep in mind the key components of symbols, expressions, and processes, and consider what their problem spaces might look like. What heuristics might this system employ? All right, thanks. Take care.